Спасибо за такое любезное представление. Только там была одна опечатка. Стартап называется Inceptive, а не Incentive, но все остальное совершенно. Да. И я буду рассказывать о трансформерах для зрения. Я этим занимался до этого в Гугле. В этом стартапе у нас биомедицинские приложения, а не зрение. Небольшой поворот. Я так понимаю, у меня 40 минут в сумме. Я попробую уложиться в 30, чтобы оставить время на вопросы, но посмотрим, как пойдет. Может быть, в конце придется немного спешить. Да, но это будет обзор не всего-всего, что произошло в зрении, а именно с фокусом на трансформерах, потому что я про них больше всего знаю и ими сам занимался. Ну и поговорю про разные темы для трансформера, для трансферного обучения, для задач помимо классификации изображений, для мультимодального и обучения без учителя, self-supervised. Вот, да, и просто чтобы упомянуть, не все статьи, про которые я говорю, я сам над ними работал, над некоторыми я работал, некоторые от коллег из Гугла, некоторые из других компаний. Просто такой обзор. И еще я буду говорить на английском, потому что, к сожалению, на русском у меня на профессиональные темы не очень хорошо получается. Уже даже на этом слайде у меня были проблемы с терминами. Но потом на вопросы отвечать, конечно, могу на русском. Так, ну все, давайте тогда начнем. First, to motivate the talk a bit, let's start from ConvNets. As you all know, for a long time, convolutional networks have been the dominating architecture in vision, starting from AlexNet in 2012, and since then on. The performance and all the benchmarks has been steadily improving. So this is, I think, ImageNet accuracy from papers with code, and there's AlexNet in the beginning, and then things get better. And same on other tasks, like this is, I think, COCO object detection, and this is, I think, semantic segmentation, maybe on cityscapes or something. So ConvNets were getting better, results were getting better. One prominent way of improving the results was transfer learning, and here is a cartoon picture of it. Here the x-axis is the number of training examples. So let's say we have a new vision task we want to learn, and we have some number of training examples from this for this task. That's the x-axis, and then the y-axis is the performance when we train on these training examples. And let's say this orange curve is the from scratch performance. So if we just randomly initialize network, train it on this number of training examples, get some number. And of course, the more samples you have, the better. And also the performance grows quite slowly. So you need quite a lot of data to get really good numbers. But then, we know that there are some vision systems, such as human visual system, which are really sample efficient. So, we humans with just a handful of new examples of a new task can do it very well. And so one way to get closer to that is this idea of transfer learning or pre-training fine-tuning. So instead of just randomly initializing the network, we first train it on some other task, pre-train it, and then only fine-tune it on the task of interest. And it turns out that if you do it, it can lead to much better sample efficiency. So you may need much fewer samples to get the same results on the task of interest. And that's what this blue curve is trying to show. And even in some cases with 0 examples, you can get some reasonable results, as that's called zero-shot transfer. For instance, GPT-3 can do something of that sort without seeing any examples of the new target task. It can already do something reasonable. So this is the idea of transfer learning and why it's useful. And then, as I already alluded to, one very prominent example of this transfer learning working out very well was in language processing. So this plot here on the right illustrates this explosion in the size of the models in language. So the x-axis is time, the y-axis is the number of parameters in largest language models. And yeah, you can see that it's, now over 1 trillion parameter in the largest models, and they are using exactly this recipe of pre-training and then fine-tuning and combined with large models that works very, very well for language. Also note that all these models are transformers or variants of them. At the same time, in vision, the scaling situation is not so advanced. Like there are some efforts, or there have been some efforts with ConvNet architectures, but that was quite challenging. And yeah, basically, back in the day when we started doing transformers for vision, the question was, can we do something similar to what happened in language, but in vision? So can we also do this large-scale training of large models in vision? And that's one motivation to try transformers for vision. Now, before diving into papers, let me real quick say a few words about general properties of convolution, which is a key building block of convolutional networks, and self-attention, which is a key building block of transformers. Convolution, which you, or many of you, hopefully know very well, it's a local operation, so it slides this little convolutional kernel around the large image, but the kernel itself is small and local and only aggregates information from a small neighborhood. An issue is that it's quadratic in compute. Because it's global, because every token talks to every token, that becomes quadratic in the number of tokens. And for that reason, if there are too many tokens, it becomes very expensive. That actually has been an issue for applying it in vision for a while, until this is not yet 2021, this is still 2020. Well, the paper came out in 2020, but this is just to motivate what comes next. The vision transformer architecture was perhaps the first successful application of standard transformers to vision. And then we feed this sequence of embedded fetches through a usual, very standard transformer encoder, and can do image classification on the output of that. And so this whole thing can be trained for image classification in supervised fashion. Right, I mean, hopefully most of you have heard of transformers, but just as a very quick recap, that's a scheme of a transformer encoder on the right. So it consists of these gray blocks, and each of them has two stages. The first one is multi-head attention, so that's this self-attention operation where every token talks to every other token, so every token aggregates information from every other token, so it's basically global exchange of information across the whole input. And then the second stage, this blue MLP, is per token processing, so that's a small multi-layer perceptron or small fully connected network that's applied separately to each location. And yeah, the whole transformer is a stack of these blocks with alternating self-attention, which shares information, and then MLPs, which do local processing. Okay, so it turns out that works pretty well. So here on the x-axis is the pre-training dataset size. There are 3 datasets of increasing size. ImageNet is roughly 1 million examples. ImageNet 21K is something like 13 million. And then JFT is 300 million examples. And on the y-axis is the transfer fine-tuning performance on ImageNet. Then the different colorful circles are transformers of different sizes, and the gray area, these are baseline ResNets, so like the previous work that did something similar with ResNets. And what we can see here is that on ImageNet, transformers look kind of okay, but not that great. But then on larger data sets, they start really shining, and especially on the biggest one, they are substantially better than ResNets. Something to note here is that this is a plot from the original paper back in 2020. Since then, others have found that with some tricks, such as strong regularization or using some special optimizers, you can actually get the results really good on ImageNet from scratch as well. So here in this plot, it looks bad on the leftmost on ImageNet from scratch, but actually it turns out you can improve that quite a lot if you try hard. And then this plot is perhaps the most important one because, as I said, we were motivated by this scaling idea, and scaling models is expensive, computationally expensive. So what we really care about is getting best performance with limited compute, so kind of best bang for the buck. And this is a plot that illustrates this. On the x-axis is the amount of compute spent on pre-training in exaflops or something, in some weird units. And on the y-axis is when you take this pre-trained model and fine-tune it on a few data sets of interest, what's the average accuracy there. And it compares architectures of 3 families: ResNets, transformers, and hybrids, which is, hybrid is a ResNet on top of which there is a transformer. And basically you can see 2 things. One is that transformers scale better than ResNets, and 2 is that on the left-hand side for smaller models, hybrids are good, but then on the right-hand side for larger models, this advantage seems to vanish. So on the right-hand side, these orange crosses and blue circles are kind of the same, which kind of suggests that when you go in large model regime, maybe specific engineering design decisions matter less, and just a generic transformer architecture can do very well already. Okay, I think with that, we're finally done with the older stuff and moving on to the newer stuff, to kind of what comes next. So this scaling vision transformers work is one very natural continuation of what I just talked about. Here, basically, the idea is to scale further, to try bigger models and see how far you can push it. And this plot here is kind of similar to the previous one, but now on the y-axis it's error instead of accuracy, so actually lower is better. And x-axis is still compute, y-axis is now error, so lower is better. And it shows a bunch of different models of different sizes, different data sets, and I guess no need to dive into depth of what exactly are the different models, but the interesting thing is that there is this fairly clear trend, more or less linear, and then towards the right-hand side, it starts to shallow out because the performance saturates. But generally, there is a pretty clear linear trend with more computation spent on pre-training. The error steadily decreases, which is nice, which is kind of a good result for this scaling story. And yeah, also turns out that with the biggest model from this experiment gets really good results on ImageNet and everywhere. It has been on top of the ImageNet leaderboard for a long time. I think maybe it is not anymore, but yeah, for a long time it has been state of the art on ImageNet. Right, and then one thing that happened after the original white paper is that there has been an explosion of interest in various transformer-based or transformer-inspired architectures for vision. This is a plot from this blog post that's linked in the slides. So there was a very nice overview blog post talking about some of those works. And you know, even here you see there's like maybe more than 10, 15 different methods, and there have been many more. So there's really quite a lot of work. And the interesting point here is that this is ImageNet from scratch. So again, the x-axis is compute, the y-axis is performance. The task is training on ImageNet from scratch, and the red blobs are the original bit, which looks pretty bad here because ImageNet from scratch is not what we were optimizing for. But then you see that the other blobs actually look really good. So people have figured out how to make things work on ImageNet from scratch, and there's really a lot going on. I have no chance to cover a large fraction of it, but you know, I'm just flashing it here, and you can look it up online in this blog post and elsewhere. Yes, here I will just highlight a couple of things. I guess one very prominent representative of this wave of work on transformer-inspired architectures is Swin transformer. It basically has a couple key ideas. So one is in VIT, we have this patch embeddings, and then from then on, we just apply the usual transformer, which doesn't do any downsampling. It just kind of processes things at the same resolution. And that's nice and clean and kind of convenient, but also from ConvNets and generally from vision research, we know that in vision it can be useful to start at higher resolution and then gradually downsample. And Swin transformer does this pyramid of resolutions idea. So it starts at smaller patches and then it gradually makes them bigger. However, a problem with that is, as I mentioned, this quadratic cost of self-attention. So if you make the patches very small, then there are too many of them and it becomes expensive. So to deal with that, they do windowed attention. So they don't attend globally, but they attend somewhat locally. Here in this left picture, the small squares are patches, and then these bigger red squares are this attention regions. So within these red squares, patches attend to each other, but not across the regions. And then one problem with this windowed attention is that then these regions don't talk to each other, and kind of the information doesn't spread across this region boundaries. And to deal with that, they do this shifting trick. So in consecutive layers, they shift these windows by half of their size, and this way there is actually exchange of information between the windows. And this turns out to work pretty well on a lot of tasks, and this is a really strong general backbone for vision tasks. And then, so the Swin transformer was like a really kind of practical architecture, and this one, MLP Mixer, is less practical, but conceptually interesting. Here, we were basically wondering how simple can one go? How much can one simplify an architecture and still have it work? This was inspired by these results we got from transformers that I mentioned, that when the models get fairly large, it seems that the engineering and design decisions don't matter that much, and even something very simple can work. And so here we wanted to see kind of how far we can push this simplicity. Basically, the architecture is very similar to VIT. So it's also embed the patches and then do these layers of per token MLP and information exchange across tokens, except that here for this information exchange, instead of attention, we used also another MLP, but applied on a transposed feature matrix. So here there is one MLP that does this per token processing, and then we transpose the feature matrix and apply another MLP that does the mixing of different tokens. And turns out that works surprisingly well. So here on the right is another one of these compute versus performance plots, and the blue triangles are transformers, the pink circles are mixers, and you can see that the frontiers covered by them are more or less the same. So interestingly enough, this very simple architecture consisting only of MLPs is quite competitive with transformers as well. All right, so that was a very quick run through the whole scaling and transfer learning story. Now I'll say a few words about some applications beyond visualization, just a few, just to highlight some interesting works, by far not everything. This transformers for dense prediction is one, where they use transformers or a variant of transformers for mostly depth estimation, also semantic segmentation, but I think the depth estimation results in this paper are the most interesting ones. Yeah, so the architecture is a variant of transformer with also some pyramid of resolutions, but let's not dive into that. And the interesting thing is that the results are really good. So here They compare the midas. This second column is a baseline, which is confident-based, and then the two rightmost columns are the transformer-based models, and they actually work quite a bit better. I mean, also in terms of numbers, but I didn't want to bore you with numbers. You can see that, for instance, in the bottom image, there are all these details in the tree branches, and also the depth predictions are smoother and more correct if you look at them carefully, which I think makes sense because transformers have this global interaction, so this global information sharing, and that seems like a really good fit for something like depth estimation, because for that you need to reason about 3D structure of the scene, and it can require very global information exchange, and I think it makes a lot of sense that for this task transformers are really good. Then people have applied transformers for video. There have been multiple papers, but this is one of them. Here the idea is very similar to VIT, but basically instead of image patches, you take these blocks of the video, and it's a bit challenging because videos are large, and so you again need to make sure that this quadratic cost of self-attention doesn't become prohibitive. But it turns out that you can do it, and especially with some tricks of factorized attention, so do it along each axis separately or such, one can make it work, and then the results are really good. Again, I'm just flashing this table. I guess there's no time to look into it in detail, but basically you can see that the vivid numbers are in bold, which means they are pretty good. Another one is point transformer. So this is about point cloud processing. And here, again, transformers are a very reasonable fit because point clouds are naturally sets. So point cloud doesn't have any pre-specified order. It's just a set of points. And transformers are set-based models, as I mentioned. So they process sets. They also don't care about order. And that makes for a really good fit. A difficulty is that point clouds are usually quite large, and again, just processing them naively with transformer becomes very expensive. But if one does something somewhat smart about starting locally and then gradually going to larger neighborhoods, then this actually can work really well, as shown in this paper. And then one more, it's a more recent application, and I think it's quite interesting one, so I'll spend a tiny bit more time on it, is the scene representation transformer. It's an application of transformers to image generation, to view synthesis. So the previous ones were about recognition, and this one is now about generating images. And the task we're looking at here is given a few images of a new scene. They may also have camera poses with them or not. So given just a few images, encode them into a representation of the scene. So infer some scene representation from them, from which you can then render all other new views of the scene. So sort of based on just a few images, understand what the scene is, and then be able to generate new views of the scene. And this is what typically 3D reconstruction is about. So that's kind of a long-standing task in vision called 3D reconstruction. From a few images of a scene, infer its 3D model and then render from that. But here we were, of course, taking a learning-based approach. And the idea was to replace the 3D reconstruction process, so going from these input images to a representation, by a confident and transformer encoder. So that's learned. And also replace the rendering part, so going from the scene representation to the image, also by a learned model by a transformer decoder. And we do this decoding kind of nerve style, more or less, where we condition the model on a ray for which we want to get the pixel value, and then, yeah, model generates the pixel value for that ray, but that doesn't really matter. Basically, take a few images, encode them into a set-based representation of a scene with a transformer encoder, and then decode images from that with a transformer decoder. And turns out that works actually pretty well. I mean, still will take some effort to scale it properly to really large and, you know, beautiful scenes. But these are some initial results, and they are, compared to some baselines, actually really good. So this is a hard task, because given just a few images of a scene, it's really difficult to generate nice and sharp views of it. So for instance, methods like NERF, they require many images, and they also take a lot of time to then train on a specific scene. While here, you just get a few images of a new scene, and you can generate other views of it right away. Yeah, I think it's pretty elegant approach, and yeah, we'll see what comes out. But I hope maybe transformers can also be really useful for this image synthesis field. Okay, that was that for a few applications, and now I'll also highlight a few works on self-supervised and multimodal learning, because I think those are really interesting areas for transformers. In language, that's what transformers were really good at, and we now see indications that in vision it's the same. So one interesting work was Dino. It more or less takes a standard-ish self-supervised learning approach for video. This sort of contrastive-like, or actually it's self-distillation type method. It doesn't really matter if you don't know what it is, but it's a kind of taking a fairly standard, more or less existing self-supervised learning method for vision and applying it to transformers. And turns out it works really well. First of all, it worked better than the same thing with ResNets. But second of all, and that's what's highlighted in this image here, is there were interesting emerging segmentations. So the model was just trained to do things at the image level, just trained to do some self-supervised task which didn't have necessarily anything to do with segmentation. But it turned out that some segmentation emerges itself in the model. Specifically, what this image shows is in different colors are different attention heads within the model. I didn't go through it in detail, so I mean, if you don't know, that's okay. But basically, in transformers, at each layer, there are several attention heads which attend independently to potentially different locations in the image. And here, in different colors, are shown attention maps of different heads. And it's really cool to see that they sort of pick out different objects in the image. So kind of different attention heads focus on different parts of the image. And that's, in my opinion, really cool, and kind of maybe promises that we might be able to learn some fine-grained image understanding without having fine-grained labels. So for instance, learn segmentation without having, you know, per pixel segmentation, ground truth labels, which are very expensive to obtain. Yeah, and also this Dino model gets really good results on video segmentation. So it shows some really interesting evidence about this emerging segmentations. And then, in language, transformers were, or kind of mostly became popular after BERT, which is this self-supervised training method where you mask out words in a sentence, and then the model has to generate them back. And this there have been a few papers in this direction in vision now, but this masked autoencoders is perhaps the most recent and the most well-performing one. So I'm only showing this one. It does a few tricks to make this really efficient, but basically it's still the same BERT. So just mask the tokens and then predict them back. And it turns out that it works really well. So this is these are some results. The x-axis is the number of parameters of the model, so it's like the model size. The y-axis is the ImageNet fine-tuning performance. And so, yeah, what they do here is that they do different types of pre-training, and then they fine-tune an ImageNet and plot the resulting accuracy here. Let's see. well, the bottom curve is a supervised bit from our original paper, which is bad, as I already mentioned, when trained on ImageNet from scratch. So that's kind of clear. Then the interesting curves are the top three. The second from the bottom, this dashed one, is supervised ImageNet from scratch. So like usual supervised ImageNet, which is fairly well optimized. Then the blue one is this BERT pre-training. And notice that the blue one is actually much better than the dashed one, which is really, really impressive. It's actually not a given, because for a long time it has been really hard to make self-supervised methods improve on top of supervised training. And now here it's way, way, way better. So this blue curve, especially for larger models, is, you know, something like 5 or 6% better than just training supervised from scratch, which is a huge difference on this task. And then it's even so good that it gets close to this dotted line, which is supervised pre-training on the very large JFT dataset. So supervised pre-training on JFT is still better, but you know, this BERT style pre-training gets really close, which is very impressive because it doesn't require all these labels from JFT. How am I doing on time? I think it has been 35 minutes, so maybe I should wrap up. Okay, clip is really cool, but maybe... Okay, well, just to say a few words, I think transformers are also really promising for multimodal learning because they are applicable to all the different modalities. So they are a great candidate for multimodal learning where you take different data modalities and process it together. Clip was one very prominent example of this, where they do image and text learning. And I guess in the interest of time, I won't go into details of how it works, but it's basically a contrastive type approach. And then it works really well on ImageNet without any fine-tuning. So it's zero shot. You train on a lot of internet data with images and text. And then without any fine-tuning on ImageNet, you get really good numbers, as shown here, especially on these like weird versions of ImageNet, like all these cartoon or sketch or whatnot. It works really, really well. So it's very robust and displays well with transformers, as they find. And let me skip this one. Turns out that with some simple tricks, you can make it even better and get even much better results on zero-shot performance. Yeah, in this whole multimodal direction, I think the SVAT work was a really interesting one because it kind of pushes it relatively far. It takes videos with audio and text, so it transcribes speech from audio and that gives text. This results in 3 modalities: video, audio, text, and then you can do a similar trick to clip, so this kind of contrastive learning where you try to embed the corresponding video, audio, text pieces close together and the non-matching ones far away. And yeah, they do it with transformers, and this works really well for them, per modality and across modalities. So yeah, this is a nice demonstration of this kind of where this multimodal direction can go, of kind of bringing all the different data modalities together. To summarize, there's a lot of interest in applying transformers to vision, a lot of stuff going on for all kinds of things. Yeah, I've only covered a small fraction of what's happening, so there's a lot more. Still, I would say it's not as far along as in language. So in language, there's this like GPT-3 or T5 type models, which really, really work for a wide variety of language tasks. In vision, you still typically need quite a lot of task-specific engineering. So if you want to, solve a new vision task, you would usually need to spend some time kind of tuning your architecture and your training process and your training data for this specific task. So I think there's still room in that respect in vision. So there's still something to learn from language for us as a community. Yeah, I think this self-supervised and multimodal training results are really promising. And yeah, overall, there's still room for exciting research. I think that's that from my side. I hope I did fine on the time, and hopefully we have some time for questions.
впечатлил, конечно, то, что этот трансформеры движутся в мультимодальные модели. Это круто. Скоро мы, наверное, увидим трансформер, который не только, как GPT-3, учится на тексте и потом говорит текстом. Мы, наверное, увидим трансформер мультимодальный, который учится мультимодально, еще и отвечает мультимодально. И текстом, и видео, и звуком. Это будет круто.
Да, хотелось бы. Это легче, как это, easier said than done. Легче сказать, чем сделать, потому что как бы технически это сложно, и эти большие модели, их сложно и дорого тренировать, но да, я надеюсь, что корпорации напрягутся и что-нибудь такое сделают.
Это будет круто. Так, у нас есть вопросы в зале, коллеги? Поднимайте руки. Так, у нас есть вопросы, а в чате я пока вопросов не вижу. Да, вот здесь вопрос. Еще, можно свет в зале, пожалуйста?
Алло, раз.
Да, говорите громче.
Раз.
Алексей,
Здравствуйте,
слышишь?
спасибо за ваш доклад. Вопрос такой. Как пионера Visual трансформеров, можете, пожалуйста, комментировать, если знаете, прокомментировать статью от наших коллег из Facebook и ConfNet for the 2020s, может быть, знаете, где они говорят, что не все потеряно для CNN. Если не знаете, не знакомы с этой статьей, то прошу прощения, что занял время. Все.
Да, но я ее не читал в подробностях, но я ее видел. Но я на это могу сказать, что я в принципе не утверждаю, что как бы ConvNets отжили свое, и трансформеры их должны заменить. ConvNets отличная архитектура, они как бы хорошо работают во многих ситуациях, и я думаю, мы еще посмотрим, да, как все выйдет. И мне кажется, что, скорее всего, какие-то гибриды будут работать лучше всего. Ну, например, тот же Swing трансформер, про который я говорил, это в некотором роде гибрид, и я думаю, что, ну, наверное, в конечном счете и те идеи полезные, и, наверное, в конечном счете какое-то сочетание их может работать лучше всего. Но в трансформерах мне нравится, наверное, вот последняя часть, про которую я говорил, self-supervised и multimodal learning. Там есть какие-то очень интересные результаты. Например, эти BERT-type pre-training, этот вот маскирование и предсказание обратно токенов. С конвнетами оно никогда не работало, а вот с трансформерами теперь внезапно работает очень хорошо. И эти мультимодальные исследования тоже. Трансформеры применимы хорошо к разным модальностям, и поэтому ими удобно делать эти мультимодальные методы. Так что, да, в общем, мне кажется, для зрения конкретно, наверное, просто трансформер не оптимален, но у них есть то преимущество, что они очень универсальны и хорошо поддаются self-supervised learning часто.
Отлично. Алексей, еще из чата вопрос от Григория Сапунова. Я переслал вам в Телеграм. Что интересного происходит с другими типами моделей, например, diffusion models или flow-based models? И уже почти все типы сетей перешли в картинки, кроме рекуррентных. Ожидаешь ли ты, что рекуррентные тоже придут в Computer Vision?
Да, хороший вопрос. Ну, как бы diffusion models, flow-based models — это генеративные модели, я про них не говорил. И, ну, это как бы... Я говорил про архитектуру в основном и про распознавание, а diffusion и flow — это про то, как их тренировать. Ну, и мне кажется, что там... Ну, вполне можно себе представить diffusion model transformer. Наверное, такие даже есть. Я этим не занимаюсь, но вполне может быть. И вообще diffusion models очень интересные и замечательные, но это как бы немного ортогональная классификация к там transformer или convnet. То есть может быть diffusion модель transformer или diffusion модель convnet. И мне кажется, да, все это интересные сочетания, и надо над ними экспериментировать, смотреть, что получится. А рекуррентные, ну, хороший вопрос, как бы, я не знаю, может быть, я что-то пропустил, и рекуррентные сети совершают камбэк, но так-то мне казалось, что сейчас в основном трансформеры их заменили в языке, так что, наверное, я бы удивился, если бы они вдруг пришли в зрение. Были работы там несколько лет назад, когда люди применяли всякие LSTM для зрения, но сейчас как-то везде утвердились трансформеры, так что я думаю, для рекуррентных сетей сложно будет их победить.
Понятно.
Нужен будет какой-то большой прорыв.
Attention is all you need, Григорий. Attention is all you need. Трансформеры пришли. Так, давайте один вопрос, да, вот последний зал, и пойдем дальше.
Спасибо большое за лекцию, за работу. И, в общем, собственно, такой общий вопрос проводит. Скажите, пожалуйста, сколько времени и человеку усилий потребовалось на идею реализации, там, не знаю, изначальный брейншторм до финальных результатов экспериментов? И второй вопрос, что делать с прямоугольными изображениями, ну, кроме как падить их там по большей стороне? Вот.
Да. Хороший вопрос. Ну, прямоугольные изображения можно просто тоже резать на патче и процессить. Я думаю, все должно быть нормально и без паддинга. Ну, у нас там есть статья про то, как ресайзить изображение. Я думаю, что этот ресайзинг, наверное, не обязательно должен быть квадратный. Хотя это, конечно, надо попробовать как-то, насколько это хорошо работает. Ну, или паддить, или не паддить, и просто посмотреть, что лучше работает. А сколько времени? Ну, саму идею-то недолго придумать. Да, все эксперименты сделать, конечно, дольше, особенно учитывая, что в первоначальной статье у нас было довольно много больших экспериментов, они занимают время и вычислительные ресурсы, и вообще как бы их сложно, может быть, сделать там вне какой-то большой компании. Ну, первые результаты мотивирующие там заняли пару недель, потому что мы просто взяли там BERT, его применили к Vision, там надо было чуть-чуть написать кода, и оно почти сразу заработало. То есть признаки жизни произошли очень быстро, но потом, чтобы из этого сделать статью, ну, это заняло там, не знаю, месяца 3, наверное, и ну, несколько человек над этим активно работало. Так часто бывает, да, что первые результаты довольно легко, а чтобы потом все довести до ума, намного больше усилий.
Точно, точно. Алексей, огромное спасибо. Друзья мои, нам нужно двигаться дальше. Алексей, огромное спасибо за то, что вы с нами и рассказали прекрасный доклад. А мы можем, кстати, мы картинку зала... Отдайте, я вас сфотографирую, Алексею хотя бы картинку зала отправлю, а то, да, а то он даже так и не видел. И вот у меня даже будет кусочек... Отлично, спасибо. Спасибо огромное, Алексей.